Hi all. In this video, we are going to learn this method of linear regression, which is actually the workhorse of most of scientific statistical analysis. So when some scientists or engineers collect data from the field or through some experiments, and then they analyze it to draw statistical inferences, most of the time what they do is this application of linear regression. So although the word linear may make it appear like a very trivial simple stuff, but it is not. It may be simple, but it is not trivial, and we will see in a moment why that is so. So to begin with, let's take a simple example of a single input parameter and a single output value. So let's say this is your input X and this is your output Y, and you did some measurements and your points, let's say, came to be following this kind of a pattern. So visually you can see that it kind of lies on a straight line which may look something like this. So you may say that my Y is equal to some mx plus c plus some error, because you can see that these points don't exactly lie on the straight line but are slightly away from it. So now this m is the slope of the straight line and this c is the y-intercept, and the job of linear regression is to use the data of these points to estimate m and c. And as we know from the video on maximum likelihood estimator, that if your error epsilon is given by a Gaussian, then you can use the least squares error method, which is to minimize this cost function, where your cost function is summation of I of yi minus mxi minus c whole square. So what do you do to minimize this? You use the concept you learnt in school. You take dou s by dou m equal to 0, and you also take dou s by dou c equal to 0, and then you will get two simultaneous equations which you solve to get an expression for m and c. So I'm not going to do it for you in this video, but I would strongly recommend to do it on your own and see the kind of expressions that you get. So now let's say your points were not exactly on this straight line, but were, let's say, following a polynomial curve. So now let's say instead of that straight line, the points that you had were on some kind of a curve like this, and this is definitely not linear, but it could be some polynomial. So it could be that your y was given by an expression like this: y is equal to some theta naught plus some theta 1x plus some theta 2x square plus some theta 3x cube, and so on up to some theta mxm plus, of course, some error term. So this is definitely a nonlinear polynomial, and your first reaction would be that this is a nonlinear problem, so there is no way that linear regression is going to solve it. But wait, don't be in a hurry. It could be that we could modify this nonlinear problem so that our linear regression still works. And that is why linear regression is the workhorse of science and engineering statistical analysis. So let's see how that is done. So what do you do is that instead of talking of just one variable x, you now talk of multiple variables, and that brings us to this domain of multiple linear regression. So what do you do? What do you do is that you now write your y as theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus so on up to theta m xm plus some error. So now from single output, single input but nonlinear function, we have now converted that into a function which is single output but multiple inputs. Now each of these input values x1, x2, x3 and so on up to xm could be functions of each other like they are in this case, or they could be independent input values. So the beauty is that this method works irrespective of the fact that x1, x2, x3 and so on are independent of each other, or they depend on each other through these functional forms. And this is what is called multiple linear regression. So this method works irrespective of where these x1, x2, x3 and so on come from. So now let's see how we can find the values of these parameters for the case of multiple linear regression. So generally we still use the gradient descent method that we learned in the previous video on gradient descent. But for the sake of theoretical understanding, it is actually possible to find a closed form solution for the theta for the case of linear regression problem. So let me emphasize once again that just because we are calling it linear regression does not mean that it cannot model nonlinear functions. So all that you need to do is that you consider each nonlinear function to be a separate variable, a separate input variable. This could be some other function also. It could be sine of x, it could be exponential of x, it could be tan of x, it could be anything. As long as you consider each of these functions to be a separate input variable, your method of linear regression would work fantastically well. Okay, so now let's see how to find these theta parameters. As I just said, in practice, you do use gradient descent even here because that is the most practical and computationally feasible method to use. But theoretically speaking, there is a way to find a closed form solution for the linear regression case. So now what we have are many data points. So actually you have yi is equal to theta 0 plus theta 1 x1 I plus theta 2 x2 I plus theta 3 x3 I and so on up to theta m x m I plus epsilon I. And now you have your cost function which is the least squares error cost function, which is what we use in linear regression, and that is given by summation of over I bracket yi minus this whole function. So in a shortcut we can write this as theta transpose xi whole square. So now this theta is a vector and these xi's are also vectors, but this yi is still a scalar because we have a single input. So this xi is a vector representing the input for the ith data point, and this theta is a vector representing the parameter values theta 0, theta 1, theta 2 and so on. So now our objective is to minimize this function s And for that, we need to take a derivative of s with respect to theta. Now in this form of s, it is somewhat difficult to take the derivative. So we are going to write this function s in a manner which will be more suitable for doing the derivative. So what do we do is that this is now equal to y minus capital X times theta norm square, and this is a matrix. So let's take a simple case for the sake of understanding. Let's say that your problem had two input variables and one output variable. So your yi is equal to theta 0 plus theta 1 x1 I plus theta 2 x2I plus epsilon I. And let's say you have a total of 5 data points. So in total you have 5 data points, which means that I is equal to 1, 2, 3, 4 and 5. That's all. In general, this number is very large, but just for the sake of visualization, we are using just 5 data points. So this S that we wrote, which is our least squares error loss function, this was y minus capital X times theta whole square. So now this matrices have to be written explicitly for the sake of better understanding. So our y is basically a column vector, which is y1, y2 and so on up to y5, representing the 5 data points that we have. Our theta is also a column vector of theta 0, theta 1 and theta 2, because we have 3 parameters. Now the challenging thing is to write down our x, which is a matrix unlike our y and theta. So now we have our theta as a column vector, theta 0, theta 1 and theta 2, and so that when multiplied by capital X must give us our required expression. So which means that we should get an expression like this, which means that this 1 x1i and x2i must form the rows of this X matrix. So now in X we should have 1 x 1 1 x 2 1, that will form the first row. So this row multiplied by this theta will give you 1 into theta 0 theta 0, x1 into x1 1 and then theta 2 into x2 1, and that plus epsilon I will give you yi. Similarly, the second row will be 1 x1 2 and x2 2 and so on up to 1 x1 5 and x2 5. This is the way you form your output vector, parameter vector and your input matrix, so that we can do our differentiation easily. So now that we have written our parameter and various input output in a suitable format, let's see how we can find an analytical expression for the estimated values for theta. The least squares error function S is equal to norm of y minus capital X theta square. So this can be written as y minus capital X theta transpose into y minus capital X theta. And now we can take the transpose inside, and that will give us y transpose minus theta transpose X transpose. So when you take a transpose of a product of two matrices, the order gets reversed into y minus capital X into theta, and now you expand this whole thing, you will get y transpose y minus 2 y transpose capital X theta plus theta transpose capital X transpose capital X times theta. Okay, great. So now what we need to do is take a derivative with respect to theta. But now since theta is a vector, we don't just have one derivative, but we have actually a vectorized quantity. So that we represent as a gradient operation, and that with respect to S gives you 2x transpose x theta minus 2x transpose y. So how we got this derivative from here is just by following matrix calculus. So I'm not going into the details, but if you're interested, there is a link in the description box which you can look into. So now our job is to equate this to 0, because that is what will minimize the function. So now once again, just by equating the derivative to 0, we get to know whether the point is a minima or a maxima. It could be either of them, but you could take a double derivative and check for yourself that you actually get a minima, because the function is a convex function. So now when we equate this to 0, what we get is that x transpose x theta is equal to x transpose y, and that gives us theta OLS, where OLS stands for ordinary least squares. This is equal to x transpose x inverse times x transpose into y. And this is the analytical expression for the parameter values given a set of input and output values. And this is what is called the normal equation. And as I said, this OLS stands for ordinary least squares. So although we have obtained an analytical solution for our theta given the input and output values, but this expression is seldom used in practice, and that is because of this inverse operation. So computing inverses of matrices is a nightmarish process, because it is computationally very expensive. So there are nowadays intelligent ways of doing matrix inverse, but still you avoid it how much ever so is possible. So generally, even though there is an analytical expression available in the least squares method, we still use gradient descent for our problems. Now again, as I have been mentioning in several videos, that although this method is very nice and works very well, but this is prone to the problem of overfitting, because if you have chosen your model to be complex enough, meaning that you took too many input values and they were complex functions of each other, then your estimation will not be proper and you will get into this problem of overfitting. And to avoid overfitting, you need to use regularization. And what is regularization? Regularization is basically moving from the maximum likelihood estimator MLE to MAP, which is a maximum a posteriori estimation. And the difference is that in MAP, you use a prior distribution for your parameters, meaning you say that I know something about my parameters, so I'm going to use that information to do my computation. So essentially what you do is that your S is equal to y minus x theta whole square. So you use basically some other function over here to incorporate knowledge of the prior information. So now, as you already know from the previous video, that the most common method is to have a L2 norm of the weight or the parameter values. So you have lambda times the L2 norm of the parameter. So when I write 2 in the subscript, that means that you are taking an L2 norm. So what is L2 norm? L2 norm is basically root over of theta 0 square plus theta 1 square plus so on plus theta m square. So usually when you do this regularization, this term is usually omitted because that is just capturing the average of your input values. So that doesn't really matter that much. So this method of regularization is what is called the ridge regularization. So in when you do regularization, you also want to divide this norm by n so that this term does not end up becoming too high. If this term is too high, then this addition will make no difference to your optimization problem. So to keep this within reasonable bounds, you do a division by n where n represents the total number of data points. So now if your lambda is very low, which means your regularization term is doing nothing much, so there you will have a problem of overfitting. So this is like not having a regularization term. But if your lambda is very high, then the higher order parameters will be penalized too much, and you will fall into the category of underfitting, which is same as choosing a very simple model for your fitting. So here you need to choose your value for lambda very carefully, and that usually can be found only by trial and error. So there are other ways of regularization also which are used in less frequency. Ridge regularization is the one which is most common, especially when it comes to linear regression, but it is important to know the other methods also. So one method of regularization is what is called the lasso. So in lasso you have the same LSE term, which is 1 by n mod square of y minus x theta square. So this is of course a L2 norm, and now instead of adding an L2 norm, you actually add a L1 norm. So this is a L1 norm. So what does that mean? That means that the L1 norm of theta is given by theta 0 mod plus theta 1 mod and so on up to theta m mod. So this is what is used when your input parameters have a non-Gaussian distribution or there are many outliers. So this is used when we have outliers and your data is non-Gaussian. So this does not happen too often, but when it happens, you need to use these other methods in order to avoid problems of overfitting. There are also two other methods that one could use. One is called the subset selection. So in this, without getting into too many details, but after doing your optimization, you basically pick a subset of features based on some threshold. So instead of finding the appropriate parameters for all the input features, you actually throw away some features which are not very useful to you. Then of course you could do Bayesian linear regression, which is a very complicated process, and generally it is not done. But in case you want to be very, very rigorous, what you could do is to estimate not just the parameters but also the errors in the parameter, or they are also called the weight values. So as I said, this is a very complicated process, but if you want, you could also do it. So these are some ways of regularization for the linear regression problem, and which are used very commonly in other methods of machine learning also. But irrespective of which method you use, it is invariably required to use some method of regularization in most problems of machine learning. So this was a simple introduction to the linear regression algorithm. In the next video, we are going to take it forward and learn logistic regression, which is one of the most popular methods of machine learning used for a very wide variety of problems. So till then, stay connected.